Okay, so again I start from where we stopped last time. We are discussing Hermitian matrices, their eigenvalues, eigenvectors, properties and all those. Okay, we also told this thing that all the eigenvalues are real for a Hermitian matrix, and if there are two distinct eigenvalues lambda 1, lambda 2, corresponding eigenvectors, they are mutually orthogonal, and you can normalize each so that the norm square is 1. In that case, they will be orthogonal, orthonormal. Right, this is what I said. Now we understand how you find out eigenvalues and all. If you are given an equation like Ax for a general matrix, not necessarily Hermitian, equal to lambda x. This is all known stuff, but still it is A minus lambda I, A matrix minus lambda identity matrix, that into x equal to 0. So therefore, for this matrix to have, if this A minus lambda I, if this matrix is invertible, then obviously x is 0, because if you call it B, Bx is 0, B is invertible, so B inverse 0, which is 0. But we are looking for non-zero solutions because eigenvector is non-zero. That means this must not be invertible. Okay, which means this determinant must not be 0. Okay, so we should find out where it is determinant. Determinant at least for some points it should be 0. So what we do? We find out the determinant of this A minus lambda I, all right, and equate to 0, and find out for which values of lambda. After all, if you take the determinant, what it will be? It will be a matrix A minus lambda I means diagonal entries. What is lambda I matrix? It is a diagonal matrix with all diagonal entries lambda. So A minus lambda I means diagonal entry from each diagonal entry of A, lambda will be subtracted, and then you find out the determinant. So the determinant will be actually a function, will be a polynomial in lambda. Okay, and polynomial order will be same as the size of the matrix. If it is n cross n, it is because it will be like A11 minus lambda, A22 minus lambda, dot 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 ANN minus lambda, and this side other elements. And if you take the determinant, finally, these times, determinant of this will come as one term. Again, that determinant will have this times determinant of this, and like that. So that product will be will involve all of them, and other products will have less number of such factors, but nevertheless, everything will be, you can understand, you will have a polynomial in terms of powers of lambda, and highest will be, if it is n cross n, lambda to the power n. So if I equate that to 0, I can solve a polynomial. I can factorize into n number of first order factors, lambda minus something and all that. So I will get n values of lambda, maximum n values of lambda for which this is 0. So those values of lambda for which this is 0, then the matrix will not be invertible. In that case only I can have non-zero solutions of x, right. So those will give you the eigenvalues. Now it can so happen that when you factorize the polynomial, which is called characteristic polynomial, determinant of this gives rise to characteristic. These are known stuff. Polynomial it could be something like some constant, maybe d0 plus d1 lambda plus d2 lambda square dot 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 dn lambda to the power n. A is n cross n. So that it will be having n terms. So you factorize in first order factors. First order factors could be like if you take, it could be lambda minus maybe some lambda 0 or lambda 1 rather. In general, lambda 1, lambda 2, lambda n will be distinct, but they can repeat also. For instance, lambda 1 and lambda 2 could be same. So you can, in that case, this factor will have power 2, lambda minus lambda 1, again lambda minus lambda 1. So when you factorize, maybe you have distinct factors, all distinct, so you get distinct eigenvalues lambda 1, lambda 2, lambda n, because if you get equal to 0, either lambda equal to lambda 1 will be an eigenvalue, or lambda equal to lambda 2 will be another one, in which this is, for which this is 0. So, eigenvalue lambda 1, eigenvalue lambda 2, etc. So, in a general case, lambda 1 not equal to lambda 2, not equal to dot 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 dot, not equal to lambda n, but there could be cases where, I mean, some of the eigenvalues can be same, so the factor will repeat. Now, I will prove something for which I will assume the eigenvalues to be distinct, that is, and I will prove something, but that result holds even when eigenvalues are not all distinct, some are repeating, but that is beyond you at this stage, so I will not prove that. All right, and say suppose lambda 1 has eigenvector say E1, and E1 norm square is 1, normalized. Instead you have seen, given any vector, if it is a non-zero vector, norm square is 1, so you can divide it by just the norm, that is, take every element of the vector, divide them by the norm, resulting vector has unit norm. So, that is doable. So, suppose the eigenvectors are already, and if E1 is an eigenvector with some eigenvalue lambda 1, any scalar times this eigenvector also is another eigenvector with the same eigenvalue, that also we have seen. So, normalization does not change the eigenvalue. Eigenvector just changes to 1 whose length is 1. So, suppose lambda 1 has this, lambda 2 has eigenvector E2, again dot dot dot, lambda n has eigenvector En. All right. So, now what I do, and none of them is a 0 vector, and remember norm square of any vector is x h x. Yesterday we have seen H is the Hermitian transposition, and inner dot product between any x y is x h y. These things were seen yesterday. So, suppose I form a matrix T by putting the eigenvector side by side, E1 eigenvector as the first column, E2 second column of the matrix, dot dot dot, EI ith column, dot dot dot, En nth column. All right. So, n vectors, and every one is length n cross 1, because matrix is n cross n. So, eigenvectors are length n. So, length is n, total number is n, so it is n cross n square matrix, right. This matrix has a beautiful property. If I do TH T, TH means, you remember this first, you have to take transpose and then conjugate. So, transposition you can easily see, E1 is a column vector, now it will become, after transposition it will be the first row. Then E2 is the second column, after transposition it will become the second row, and likewise. So, after transposition it will be E1 column vector. So, now row version is E1H, because you have to transpose and conjugate, because TH means you have to apply H on this, okay. That is, you have to you have to take transpose of this matrix and conjugate every element. Ordinary transposition means what? You can easily check that all the elements here, they will go here. So, first column will become first row, and then conjugate, because I am looking for TH. So, not just conjugation, not just transposition, but conjugation. So, it will be E1 made into a row from column and then conjugated, every element conjugated. So, that is nothing but E1H, it will be a row vector. Then second column, all these elements, they will be the second row after transposition, and then conjugating each element. So, it will become E2H dot dot dot, EIH, ith row. And dot dot dot, ENH, nth row. This is your TH, and then T is this. So, what will be the product? Let us start with this E1H E1 row vector column vector, that will be the 1 comma this element, this row times this column, but E1 comma E1H E1 is norm E1 square, okay, XHX is norm X square. So, E1H E1 is norm E1 square, which is 1 normalized. E1H E2, this is a dot product between E1, that is inner product between E1 and E2. X dot y means XHY. So, E1H E2 means E1 dot E2. We have already seen. So, E1 corresponding to lambda 1, E2 corresponding to lambda 2, and they are not same, therefore, they are orthogonal. So, E1H E2 will be 0. Next will be E1H E3, that will be 0, dot 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 E1H En will be 0. Then E2H E1, that will be this guy. Again, it is 2, it is 1, and corresponding eigenvalues are distinct. So, for E2H E1, which is the dot product between E2 and E1, that will be 0. Then E2H E2, E2H next column E2. E2H E2 is the norm square of E2, which is again 1. Then E2H next column E3, that is 0, dot 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 E2H En 0. Similarly, it will be like this, it will become 0 dot 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 0 dot 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 0 dot 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 all. So, it will be basically identity matrix. So, this is a property, that is TH T is identity. So, T is a square matrix. So, TH also square, because you take transposition. So, it was originally square n cross n. So, after transposition also n cross n, and then just conjugated. So, square matrix, square matrix. I told you the other day, if there is a square matrix such that if A and B are suppose two square matrices and their product is I, then one is the inverse of the other. That is, B is A inverse, so that A inverse is I, and A is B inverse, so that B inverse B is I. They must be square, and the product should be I. Then one is the inverse of the other. Okay. So, that means here TH is T inverse and T is TH inverse. Such matrices are called unitary matrices. UNI TARY. The beauty is, if you want to calculate the inverse of this matrix, you do not have to carry out all those in detailed steps. Just take the given T, take the Hermitian transpose, that is conjugate every element and transpose or transpose and then conjugate, resulting matrix will be the inverse. Unitary matrices, that is for T is an unitary matrix, means its inverse is nothing but its own Hermitian transpose, that is THT is I, and therefore TTH, that is also I, because one is the inverse of the other. So, THTI, TH is the inverse of T, so T inverse here, which is I. Okay, this is called unitary matrices and very, very useful in signal processing. All right. So, if the eigenvalues are all distinct, I get n number of normalized eigenvectors and they are mutually orthogonal. So, if I construct a matrix T by putting them together side by side, TH is and T product is identity, that means this T becomes unitary matrix, right. Next, another property of unitary matrix, suppose Tx, x is a vector, T is unitary. Suppose unitary, T A or Y, unitary. Then Tx, if you are given x, you apply T on this T on it, call it Y. Norm square of Y will be what? We all know YH Y. There is the length, square of the norm or square of the length of Y will be nothing but YH Y, and Y is obtained from x by this transformation, T working on some given x giving you Y. So, if I replace Y by Tx H and again Tx, So, it is XH, TH, then TX, but T is unitary, means TH, meaning TH, T and TTH, their identity. Okay. So, this THT, it is identity matrix. Identity matrix to X is X, XHX is back to the norm square. So, if Y is obtained from X by applying on X a unitary matrix, then norm square of Y and norm square, original norm square of X, they remain same. So, unitary matrices preserve norm. It can change a vector X to Y, but length does not change. This is another property. All right. So, now suppose A matrix was given to me, which is Hermitian, and AT. I am taking that same A matrix as earlier. It has n number of distinct eigenvalues. It is n cross n matrix, and I am assuming all the eigenvalues to be distinct. So, eigenvalues were lambda 1, lambda 2, dot 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 lambda n, corresponding eigenvectors were E1, E2, dot 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 En. All these vectors are normalized, there is norms is 1, norms are 1, and they are mutually orthogonal. So, they are orthonormal. Then using them, I constructed the T matrix by putting those eigenvectors side by side. T was E1, E2, just I am repeating for your sake, En. This T is unitary. Then what happens to AT? AT means A on E1. A on E1 is lambda 1 E1. Then next column will be A on E2, which is lambda 2 E2, dot dot dot, lambda I general column EI. Dot 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 lambda n En. Okay. Now, I tell you something, a side story. Suppose I give you a matrix A1 1, A1 2, just 3 by 3, A1 3, A2 1, A2 2, A2 3, A3 1, A3 2, A3 3, and I multiply by some elements C1, C2, C3. We all know how to do it. A1 1 times C1 plus A1 2 times C2 plus A1 3 times C3 will be the first element of the realtic vector, column vector. Then A2 1 into C1, A2 2 into C2, A2 3 into C3, summation will be the second element, and A3 1 C1 plus A3 2 C2 plus A3 3 C3, summation will be the third element. But we actually do not, carry out matrix into vector multiplication in those manners anymore. When we reach this stage, we do not, and from today I hope you will also not. You will see that this is nothing but, if you take the first column of this matrix A2 1, A3 1, if I multiply this by C1, all the elements multiplied by C1, then take the second column A1 2, A2 2, A3 2, multiply all the elements by C2 and take the last column A1 3, A2 3, A3 3, multiply by C3. Then if you add, you will see A1 1 C1, A1 1 C1, A1 2 C2, A1 2 C2, A1 3 C3, A1 3 C3. So, you get the first element which you are getting here. Then second A2 1 C1, here A2 1 C1. Okay, A2 2 C2, A2 2 C2, A2 3 C2, A2 3 C, A2 3 C3, A2 3 C3. Their summation. So, you get the second element like that. This is what the actual meaning of matrix into vector multiplication. That is, you take the columns and linearly combine them by those coefficients. Let's take the first column, multiply by the first element. Take the second column, multiply by the second element. Take the third column, multiply by the third element, like that, and add. It is called linear combination. Linear combination of the columns by C1, C2, C3. All right. So, using this right hand side, I can write like, you just see E1, E2 dot 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 En, and I form a diagonal matrix, and this side 0. That is all the elements here are 0. This is a big 0. All the elements here are 0. That is the diagonal elements. You can verify this equal to this, because we will be, so just consider this matrix times the first column, like this matrix times the column vector. This matrix times this first column. What it will be? It will be lambda 1 times E1, then below is 0, 0 times E2, then below is 0, 0 times E3, like that, and their addition 0, 0, 0, lambda 1. So, it will be lambda 1 times E1, others are getting multiplied by scalar zeros, so they go. So, lambda 1 E1, that is what you have here. Then again take the second column, this second column. First guy is 0 here. So, this matrix times this second column vector will be what? Is 0 times first column E1, lambda 2 times second column E2, then again 0 times next, dot 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 0 times last. So, lambda 2 into E2, only that will remain, and likewise. Okay, just use this. But what is this matrix? This is good old T by definition, the T I constructed, E1, E2, En, and this is the diagonal matrix with the eigenvalues, distinct eigenvalues of A, and they are all real because A is Hermitian. So, it is a diagonal matrix consisting of all the distinct eigenvalues, okay, and eigenvalues are real. So, I call it D, D for diagonal, so matrix T. So, that means I have an equation A T is T D. So, suppose I do A T, I multiply this by T H. After all, A T is a matrix, T H is a matrix, so I can multiply them. So, here also T D T H, but T T H is identity, T T H is identity because they are unitary. So, it becomes I, A into I is A. So, in this case A can be written in this product form. This is a very important result, product form, or sometimes called factorization of A. So, it is a product of 3 matrices, as though I factorize into a product of 3 factors, T factor, T is a factor, D is a factor, T H is a factor, factorization, where D is a diagonal matrix, T is a unitary matrix. All right, this is a beautiful result, I will be using it later. If A is Hermitian, this is always doable. This implies 2 things. Given A equal to T D T H, number 1, determinant of A will be determinant of this product, which is determinant of T into determinant of D into determinant of TH. But TH is same as T inverse, and determinant of T inverse is 1 by determinant of T, and that cancels with this. So, you are left with determinant of D. And what was D? D was the diagonal matrix of eigenvalues. This side 0, this side 0, big 0. So, determinant of this matrix is nothing but product of the eigenvalues. Product I denote like this, I equal to 1 to n lambda I. There is lambda 1, lambda 2, lambda n. Which means, if every eigenvalue is non-zero, then determinant is non-zero, which means the matrix is invertible. On the other hand, if A is Hermitian and it has at least one eigenvalue 0, then determinant is 0, which means the matrix is not invertible. Understood? Okay, matrix is not invertible. So, A is Hermitian, and in that case, if A is given to be Hermitian, in that case, if all the eigenvalues are non-zero, positive or negative does not matter, but if they are non-zero, determinant is non-zero, so they are invertible. But if any eigenvalue or even a single eigenvalue becomes 0, means determinant is 0, so matrix is not invertible. Another property called trace. Trace of a square matrix, if I give you a matrix, say D, not D, D is used here. say if I give you a matrix, say R, say n cross n, okay, it's a square matrix. Its trace means trace, T-R-A-C-E, trace, T-R-A-C-E, trace. I am writing T-R dot. Means you just sum up all the diagonal elements. That is R, its ith diagonal element. You can forget this m cross n here. This is just to indicate the size. So I equal to 1 to n. That is R11, R22, R33, 44. So those are the diagonal elements. Sum of the diagonal elements is called trace. Now suppose R is A, B, where A can be, A is maybe n cross some m and B is m cross n. So n cross m cross n, product is n cross n, that is what R. Then trace of AB will be what? Trace of R is this, summation RII. But what is RII? R is obtained, R is like this, A and B. So Ri comma I will be what? Ith row of A times ith column of B. Okay, ith row means AI1, AI2, AI3 like that, and ith column means A1 comma I, 2 comma I, 3 comma I, and they are multiplying and getting added. So RII any RII will be what? AI1, B1I, AI2, B2I, like that. So they are summation. So AI bring an index K, K1 to n, AI1, so then B1, K is 1, then B1, BKI. If K is I, K is 1, AI1 here, B1J here, 1I. Then if K is 2, AI2, B2I here, and like that. So this times this, next times next, next time like that, and their summation. All right, this is the trace. Now, that means trace of R is double summation IK BKI. Now, see, this double summation has a property. What is happening? First you are fixing I at 1. Then for that I you are putting 1 here, then you are running K from 1 to n. There is 1 to n, 1 to n. Then you are taking I equal to 2. So first you took I equal to 1, I equal to 1. And you run K from 1 to n, K from 1 to n. Finish this summation. Then move I to 2. Again run K from here, K from here. Okay. Finish. And like that, and then you are adding. You will get the same thing if you first fix K at 1 and move I over this range, then again K here, move I over this range, and same here. Okay. So you can interchange the two. Instead of fixing I first at a value and then moving K over the range, you can fix K over a value, then move I over the entire range, then take the next value of K, again move I over the same range, and so on and so forth. You will cover the same grid, I equal to 1 to n, K equal to n, all the points, integer points, for I and K, that will be covered. So which is nothing but called interchanging the summation order. That is, first you take summation over K, which means every time you give a value to K, hold that fixed. For that, move I equal to 1 to n. Again another K, hold that, and then move I to 1 to n, like that. This does not change, but I will for convenience write B first, BKI AIK. What does it mean? It means this. Suppose I have, instead of AB, I had BA. kth row and kth column. So, product matrix I am finding out say k comma k, kth row kth column here multiplying will give me, if the product matrix is something called G. So, G k comma k, kth diagonal entry I am finding out. Suppose what will be the expression? B k comma 1, say k 1 and then 1 k, a 1 k, then B k 2, a 2 k, again B k 2 because k is fixed, a 2 k, and likewise, isn't it? So, this will be, if you call it this matrix B A as say G, this will be G matrix, it is k comma kth element, where G is B A. Okay. So, if you take the product, call it G, it is kth diagonal element, and now you are summing all the diagonal elements 1 1, 2 2, 3 3, 4 4. So, it is nothing but trace of G, and G is B A. So, trace of B A. This proves the result, and R was A B. So, this trace of A B was equal to trace of R is A B and up to here. So, trace of A B is same as trace of B A. Okay. Trace of A B is same as trace of B A, and A is this. So, next thing that we do today is you are giving the matrix A S T D T H. Okay. And if you have to find out the trace of this square matrix which is Hermitian, trace of A, it is trace of T D T H. Okay. You take this matrix to be maybe x and y. This is what DTH suppose is y and this is x. But we have seen trace of any xy is same as trace of yx. So, you can bring DTH first and T second, but then now THT if you combine this identity, this is unitary matrix, D into identity is D. So, trace of D. What was D? D was a diagonal matrix with these eigenvalues of A, other elements are 0. So, trace is just summation of the eigenvalues. And remember, eigenvalues are real. So, if A is Hermitian, this is another property, its trace is summation of the eigenvalues and therefore, trace is real. Okay. Trace of R, trace of A is this, summation of the eigenvalues. All right. So, I stop here today, and we have covered some good properties of these Hermitian matrices. There is a special class of Hermitian matrices called positive definite matrices. So, I will just cover them, it will take 10 minutes or so, and then we will go to random process, random waveforms and all that. With that background, later we will move to optimal and then adaptive filters, and then some examples, and then again back to adaptive filter, higher versions of adaptive filter and all that. Okay, that is all. With that, thank you very much and goodbye from here. Bye bye.